Yeah, today we'll talk about so-called zero knowledge proof technology and its use cases where we can use it. From my own experience, this is the most complicated technology which exists in blockchain technologies, in blockchain family, I would say, protocols and technologies. So let's try to understand how it works. So first, what it is. So what are zero knowledge proofs? Zero knowledge proofs is a way when we prove something as a prover to the verifier without disclosing our private or internal secret information. Which means that the verifier, the only thing verifier will understand from information, the data, the proof that we provided to verifier is that if our statement is true or false. So strictly speaking, zero knowledge does not mean that no one understands nothing, but zero knowledge means that there is an exchange of data, there is an exchange of proof between the prover and the verifier will understand if what we say is true or not. Why this technology is complicated? Because common sense, our human common sense does not work like this. So it's hard to understand how it's possible. For example, you may come to a shop, buy an alcohol, and actually, if you provide a zero knowledge proof that you are older than 21 years old, it means that the verifier, the seller of alcohol, will understand from zero knowledge proof that you are actually older. That's it. That's all that verifier understands from information that you provided. It means that there will be no correct information that you are 22 or 25 years old. So that's the key point. Why we use zero knowledge proofs? The other thing that, strictly speaking, we do not need a blockchain to work with the zero knowledge proofs. Zero knowledge proofs technology may work without any blockchains, but it's very useful for the blockchains and for two key reasons. First, it's scalability. It means that when the proof is generated, it's quite complex, computational intensive task, but the verification is very simple. It means that we can verify information on chain. It means that we can use the smart contract which receives this proof, and this smart contract checks this proof. And if, let's say, the answer is yes, then something happens. If the answer is no, then it doesn't happen. So this proof is done on chain. So that's the key advantage of this technology. And the second point why we need it on blockchain is the privacy. It means that we know that all key blockchains like Ethereum, for example, are open. It means that anyone can read any information. But sometimes if we talk about identity, we do not want to disclose our personal information. We do not, if we, let's say, buy alcohol online via smart contract, and actually the smart contract doesn't see us, it does not understand if we are older or not, but from this proof, the contract gets the answer that yes, we are older, and let's say this alcohol will be shipped to us via email, via simple mail service, for example. And looking at this information on chain, no one will understand what really happened. So reading this information is possible to do via zero knowledge proof. completely private exchange of information. It means that it will be open, but this data, if you are not smart contract, if you are not proof or verifier, no one will understand everything and will not get any information from the exchange of this data. So let's understand how it works in comparison with the classical proof. So in classical world, for example, if I am a driver, I have a driver license, which is issued by government agency, and police stops me on the road. So it's a verifier, I'm the prover, I provide my ID, my license, driver license to police. Then police looks at it, police sees that my name, date when it was issued, my photo, everything about me. And actually, the police may check if my ID is real, if it's not faked. And there is an exchange between database of this government ID agency and the police. And after reading the serial number of this driver license, the policeman will understand that, yes, that's real driver license, and then something happens with me. What happens with the zero knowledge proof? Actually, in the same way, there is an issue. So it's the, let's say, government ID agency, which issued to me the so-called claim, which is the driver license. And actually, if policeman stops me and only asks if I have driver license or not, I may issue the proof. It's actually not the driver license itself. I will not pass my license to someone else. I keep it with me. What policeman gets, he only gets the data, the proof, from which policeman understand that, yes, I have driver license. Only answer yes or no. If I do not have driver license, then I'm stopped and fine. If I have, let's say he will let me go where I want. And we should understand that in this case, in the zero knowledge proof, there is no exchange between government ID agency and the policeman. They do not exchange the data. The only data policemen have is the data I provided as a proof, and that's it. And as I already said, even smart contract can verify this data. So it doesn't mean that it's not a policeman, it's really a program, on-chain program, very simple one. And this program can also verify my data and have the answer yes or no regarding the question that it was asked, actually. So let's look at the comparison between zero knowledge proof and classical ID. Zero knowledge proof is trustless, so it's built on blockchain and smart contracts protocol, so you don't need to trust anyone. There is no exchange between different ID agents, issuer, and the verifier. Classical trusted brick and mortar intermediates, it means that in classical way, if we have IDs, we always use this intermediary. For the zero knowledge proof, it's open ecosystem. It means that all the guys are open, anyone can use it. It's easy. For the classical ID, it's always locked, centralized, secured by firewalls, and we know that often some data about IDs, about some, I don't know, passports, licenses, whatever, there is a leakages, and the databases completely go somewhere, sold on the dark net, and etc. etc. So it's not very good. With zero knowledge proof, you are the owner of your ID, and it's not possible to steal 1 million of IDs because everyone keeps his ID with his address. And other actually quite useful qualities that zero knowledge has in comparison with classical identity. The key one, I would say, that the ID owner and verifier changing data for the zero knowledge proof. For the classical ID, the issuer exchange with the verifier, and your data, actually ID data, personal data, might be exchanged by the issuer with whoever issuer wants without asking you even permission. Actually, how it started, the history of zero-knowledge proof started with so-called, it's a relatively new, let's say, mathematics. So it's based on very complex mathematics. It only was opened in 1988, and the first zero-knowledge proofs were so close. Before that, they were interactive, and now we will talk in our presentation about non-interactive zero-knowledge proofs. What it means that in interactive proofs, there is a few exchanges between prover and verifier. So it means that there has to be a number of data which exchange. So prover sends information to verifier, verifier asks for additional information, then prover sends more information, then again. And only in this way, it was possible to check if the proof is correct. But in non-interactive zero-knowledge proof, we do not need this exchange. We only need the prover generates some data, the proof, sends it to the verifier, and verifier enough to check only this information. Verifier do not need anything else, any additional confirmation, any additional data to understand that some statement is true or false. So that's the key point here. How it works in terms of, let's say, programming. So if we dive into the details, we see that we have some private input, which we want to hide. No one should know it. We do not want to reveal this data. We have some public output. Public output is information that is open for everyone. Everyone can see it, use it, and do with it whatever he or she wants. And we have some so-called deterministic program, a circuit. That's a mathematical program, that's some algorithm, which actually converts private input into public output. We should understand that we only can do it from private to public. We only can derive public output from the private input, but we cannot calculate private input from public output. So it's not possible to go vice versa. So what our prover is doing, he's using the special function called f, using circuit, that's this program, and his or her private input to generate some zero-knowledge proof. Zero-knowledge proof is just data. And the verifier may use this function v, where he uses our calculate zero-knowledge proof. Deterministic program circuit is also open, so it's public, everyone knows it. And public output. And from these three sets of data, our verifier may understand if what we trying to prove true or false. That's it. So we see that where in this zero-knowledge proof is actually happened, that we did not disclose our private input to verifier. That's the essence of the whole technology. We only have some public data from which our verifier can understand if what we state is true or false. The example is with the hash. You already studied what the hash is. Actually, the hash is the function which transfers some data, which we call R, to hash R. It's not possible to calculate R from hash. You only can do it in one way. And we generate the proof F that with this circuit, for example, algorithm SHA-256, in our private input R, and the verifier may understand if we know this R or not. It means that from our proof, it means that, for example, if we stolen the hash of R from someone, but we do not know this R, initial R, we will not be able to generate the proof, the correct proof. And it means that the verifier will understand that we've actually stolen hash and we do not know the real R. So that's the point. We do not reveal this R, but the verifier having proof, having the algorithm, it's open, everyone knows how this hash is calculated. Having our hash, we understand that yes, we do know, we know this R, but we do not reveal this R to the verifier. This is how it works in a real, let's say, functions. So the input, you see that there's a lot of inputs. Part of them is private information, and we can check taking free data and verify if our statement, our proof is correct or not, if true or false. What else? That's the real elliptic curve. There's a formula of elliptic curve. Why I show this? Because all zero knowledge proofs are built on so-called elliptic curves. And for specific Iden3 technology, which we will discuss in our presentation, is based on so-called Jubjub elliptic curve. And it's just the function, simple function, you know them from school. And this function really produces so complicated technology. What are ZK-SNARK? ZK-SNARK is the zero knowledge succinct node and directive argument of knowledge. So this is actually one of the types of zero knowledge proof, which are now used by identity management systems, by some ZK Rollups. And actually, what it gives us, this is exactly what we have when we're using non-interactive technology. So our verifier generates this ZK-SNARK, and then verifier having this ZK-SNARK may understand if our statement is true or false. The only thing that you should know about ZK-SNARKs is that they require so-called trusted setup. That's, let's say, a weak point of this technology. Why? Because before we start this exchange of information between prover and verifier, we need to generate a so-called shared key. It should be generated once, only one time, and then this shared key might be used by anyone in this schema, in this technology. And the prover and the verifier, and whatever number of provers we have, whatever number of issuers, verifiers we have, all should use the same shared key. The point is if that we discovered somehow the private keys from which the shared key was generated, then it's possible to generate false proofs. So we should make sure before we use ZK-SNARK that this shared key was generated in a real secured manner. That's the point. But we already have more advanced technology, which is called ZK-STARKs, not SNARKs, but STARKs. And this technology is working without shared key, but it's more computationally extensive. It requires more, let's say, time to generate proofs, so it's more complicated because it's more math inside. Now we go to the use cases. There are 3 key use cases if we combine zero knowledge technology and the blockchains. That's first identity management, zero knowledge rollups, and private accounting systems. First of all, that's the blockchains which let actually hide the sender and the receiver of the tokens. Let's start with identity management. And the most advanced in this technology now is actually Iden3 technology, which is developed by Polygon blockchain company. And this is for you an example. I just found it in the news on my newsline that the Britain should be given digital ID incorporating passport, driving license, tax records to everyone. It means that I think that in the future, I don't know how many years it will take, maybe 10, maybe 15, maybe it could be quicker, maybe we will need 25 years, but in the end, zero-knowledge technology will be used for our digital identities. And that's just the first signs of what is going to happen in the future. So what is digital identity? Digital identity is when one person can define and have many identities. So it means that this technology will be really distributed. It doesn't mean that only government agencies will provide identities, but actually anything can be an identity. On Ethereum, an identity is so-called externally owned account. I think you know it, or smart contract. What else? The claim is actually, it's the document. It's this is something that identity is issued to another identity. So it means that claims create a relationship between identities. So let's say if I'm your friend on Facebook, the Facebook is actually made this relationship between you and me. But if we will try to do the same thing with zero-knowledge proof on blockchain, you may create the claim for me that I'm your friend. And I may, with this claim, issue proof to anyone else that yes, I'm your friend. I'm your friend. That's it. Claims can be public or private. And the proof, actually, this is what happens. As I said, it could be, they can be used on-chain, then it's possible to use them off-chain. So blockchain, strictly speaking, is not required. It let us keep privacy, and very important thing that it could be non-reusable. It means that only identity, the user, the prover, and the verifier may use this proof and draw some conclusions from this proof. But if someone else uses the same proof, it will say nothing about our relationship, about what I'm going to state. So Iden3 Standard is using this baby Jubjub elliptic curve, and it's developed actually the language for writing this mathematical circuits, these programs for which we actually issue our proofs, and so it's privacy by default. It actually may be used as a self-sovereign identity. That's the key management and scalability. Why scalability is important is that when we talk about blockchains, we understand that writing any additional information on blockchains is quite expensive. So zero-knowledge technology will let us provide one value, and this value may contain millions of IDs. And how we achieve this? We achieve this via so-called Merkle tree. I hope you know from the previous presentations, from the previous lectures, what the Merkle tree is and how it works. So actually, we have all our IDs written into this Merkle tree, and on chain, we keep only the root of the Merkle tree. If we add additional identities, then we actually should send only one transaction. This transaction will change the previous route to the new one, and that's it. So we can really add, modify millions of claims in a single transaction. So that's the power of zero knowledge proof and the blockchains when we combine these two technologies. Non-reusable proof, that's what I was talking about. Zero knowledge proof will lets us provide the proofs which will only can be used by our specific verifier, not anyone else. How it works, you may read later. So it's quite complicated. It's not, again, in a common sense to understand how it works, but we should only understand what it can do and what it cannot do. So we can generate again the proof for specific verifier address, and only this address with this private key may check this proof and understand if our statement true or false. If the same proof we send to other verifier with a different private key and public key, this second verifier, another one, will not be able to use it. So it's non-usable. Only our specific verifier may use it. That's the point. That's the example of implementation zero knowledge proof technology with the voting system. That's actually what our company did for one of our clients. We have an issuer, we have the voter. That's actually an address, the prover who votes for something. Let's imagine that the voter requested identification from the issuer. After KYC, issuer issued the claim, zero knowledge claim. Voter received this claim, keeps it in his or her wallet, and then our DAO, let's say voting organizer, have some poll. So from this poll, we should make some decision, yes or no, whatever decision. And we're talking about claim about the actually proof that yes, our voter is a DAO member. Everything else is happening on blockchain, on chain, on the contract. When we, as a voter, are sending transaction to our voting contract, and in this data, in this transaction, we actually send ZK proof that yes, we are a DAO member, and we send our decision. We vote yes or no for this specific poll. And the contract, without anyone else getting this information, receiving it in transaction from us, will understand first that after checking this proof as a verifier, the contract will have information that yes, for example, we are the DAO member, and if we are a DAO member, then this contract actually accepts our voting. That's it. It means that this voting procedure is made completely on chain. It's not possible to, let's say, fake the voting because everything is on chain, and the contract is working. It's a program. It's working according to its algorithm. No one can actually intrude and count the votes yes to no, and vice versa. So where we can use the identity, it's some control, physical or logical. It's a so-called single sign-on, decentralized applications, Internet of Things, anything else, any centralized applications. Signing documents and private messaging, voting, that's the use case which we just talked about, and token transfers for KYC identities. How it might work. For example, we specify a list of addresses which may request from us transfers. And again, our smart contract checks the proof which we got from some address. And if this address is, let's say, whitelisted, then we send tokens to this address. If not, then we do not send. And all this exchange is private, and no one from outside looking at these transactions will not understand actually what happens. Second implementation and use case for zero-knowledge proof technology is so-called EVMs. It's Ethereum virtual machines. Today, we have, you see it on the list, and the state validation, two major, let's say, technologies for ZK, for Ethereum solutions and rollups. So it's ZK proof, which is the majority. And the second one is optimistic one. We will not talk about optimistic today, how it works, but I should only say that they are today the most, let's say, used, because ZK is more complicated technology. It's not completely ready yet. And therefore, on top of our list, we have Arbitrum 1, Optimism. That's the optimistic rollups. All other, the majority of rollups, DivideX, ZK-SNARK, StarkNet, they are all ZK-Swap, they are all actually ZK rollups. What happens and why we need this zero-knowledge proof in our EVMs? The point is that initially, what we want from rollup is the fact that we want to keep security of Ethereum, of the L1 Ethereum blockchain, the native one, for our rollup. But how to do it? And ZK gives us an answer. So if we have some blockchain, separate one, which produces blocks, which accepts transactions, something happens in these blockchains. But we, in the end, want to collect all these transactions, the block data, put it in a circuit, generate some proof, and then send this proof to the initial Ethereum, the Ethereum special Ethereum smart contract. And this Ethereum smart contract, after getting this issued, this generated proof from our ZK rollup, will check it and verify that yes, on our rollup, each transactions was generated according to the EVM, Ethereum virtual machine rules, that no, not even one rule was broken. So that's the whole idea behind ZK-EVMs. So after this smart contract on initial Ethereum accepted our proof, our verification, we might state, we can state that our separate blockchain generated transactions according to the rules. No one broken any rules, and everything is going according to the rules of EVMs. That's the point. Another thing that it's really complicated to generate this type of proofs. And here we have actually the classification of this classification is provided by Vitalik Buterin, the founder of Ethereum, in which we see that there are 4 possible, even 5 possible types of ZK-EVMs, starting from the first to the fourth. The first one is completely compatible, but it's really low performance. And the last one is, let's say, partially compatible, but in terms of performance is quite fast. And if we speak about the fully Ethereum equivalent ZK rollups, I should say that today, still, we do not have even one fully Ethereum equivalent ZK rollup, which is working in production environment. Very close to the two projects, the Scroll and the Polygon ZK rollup, which is developed by Polygon. It means that everything is calculated and working according to the initial Ethereum virtual machine rules. So that's it's perfect compatibility. And whatever program, Ethereum program, which is written in Solidity language, you put into this Ethereum virtual machine ZK rollup, it will work. That's the full compatibility. The second type, let's say, is less compatible. There are certain differences. Let's say that the third one, which is 2.5, let's say, it has some already differences. So it has different gas costs. So it's less compatible. And if we move to the last one, to the fifth one, we see that the advantage of this approach, which it's very fast for the prover to generate the proof, but it's more incompatible. And we see that the whole list of incompatibilities, it does not support some ERC contracts, wallets. It has even some ZK-EVMs is a different language, different from Solidity. And if we look at the whole project, we see that, as I said, the Scroll, the Ethereum, that's the initial blockchain. That's the layers of this language is that we have the language level, then the bytecode, which is generated from the language, and then the runtime environment, actually the program itself, the core of the blockchain. And for the Scroll, and we have now not Hermes, but the ZK Polygon EVM, which is also completely compatible with the EVM, with the Ethereum virtual machine. And the StarkNet is less compatible because it has different it has different bytecode. You should convert Solidity into another Cairo language. You may write, I think, the programs, the smart contracts in the Cairo specifically, directly, so it's not required to write in Solidity. So, but the advantage of the StarkNet is that it's very fast. The advantage of the Scroll, it's very difficult to actually to create this technology, and then it takes more computational resources to calculate these proofs. That's the time when we will see ZK-EVMs, but already we are expecting Polygon, the type 1 actually EVM on the testnet on the 27th of March this year. Further, I don't know, but these dates are moving to the second quarter, to the third quarter, and so on. Again, how ZK-EVM works, we have this circuit transaction processor, we have old root, old state, we have new state, and we have transactions getting in. Then these transactions 1, transaction 2, transaction 3 gets into our blockchain. That's actually the circuit, and then we calculate new root, new data, and this new root is sent to the Ethereum blockchain, and this proof of this root is checked by the contract, and this is the way we prove that everything was according to the rules of the EVM. So, and the third technology use case for ZKs is so-called private accounting systems, and I think the first example is ZCash. So it's completely different blockchain, which is written according to ZK technology. It's not compatible with Ethereum, nothing. nothing similar with Ethereum. And how we would create this private blockchain. Why it's private? Because looking onto blockchain, onto blockchain explorer, of course you will see the transactions, but from these transactions it's not possible to understand and calculate somehow the sender address, the receiver address, and even the amount which was transferred on these blockchains. That's completely different from the Bitcoin, because you can see everything in Bitcoin and how Bitcoin works. Let's imagine that we have one Bitcoin on each address, and the only thing we need to keep on chain is that this one Bitcoin is owned by, let's say, public key 1, node 1, that's the first Bitcoin. Node 2, that's another Bitcoin, is owned by public key 2, and node 3 is owned by public key 3. Of course, with every public key, we have a pair of the private key. And then if we send from our public key 1, that's the Alice address, to the Bob's address, public key 4, what happens on blockchain is actually we issue new node, node 4, which is equal to public key 4, public key 1, public key 1 here. We simply erase it from the blockchain. It's no more. Public key 1 does not own our Bitcoin. So that's how actually we move our tokens in Bitcoin. Now we come to the privacy. The first step, what we do is that we add to each node, to each our node, additional value, call it serial number, R1, R2, R3. And one more step to privacy on our public nodes, which actually work with the transactions. We keep not the clear public keys, but we keep the hashes of nodes. If we keep hash, you know that from hash 1, hash 2, and hash 3, you know that you cannot understand, you cannot calculate the real value of public key from the hash value. So that's the privacy already. Here, we also need to keep on-chain not only the hashes of the nodes which owned by some address, but we also keep all the hashes of all the nodes which do not keep, but kept them in the past. So that's how our database is created on every node. Then how do we transfer the transaction? How do we make this transaction privately from one address to another? We, in fact, send this transaction to the fourth node, create this node, send it to the new address, and then we add the nullifier. So we write to our blockchain the hash that this R1, so our first address, node 1, does not more exist. And this money came to the new address. Looking onto the data on the public nodes, we do not see any information which give us understanding of who are the receiver, who are the sender of the transaction. So that's the idea. And where we use the zero knowledge proof is actually on how we prove to the public nodes that we have the right to send these transactions. So that's where we use zero knowledge proof. Because if we did not have this technology of zero knowledge proof, then as soon as we send to public node the data that I are having a certain address, sending data to another address. So it means that we reveal our addressed to some public node, and that's bad. That's not privacy. We can use the properties of zero knowledge proofs to ensure that no information about our public key, about our secret key, about our nullifier error value are revealed by us, by the standard of transactions. But that's the very simplistic explanation of how it works. Really, in reality, it's much more complicated. And one of the things that we should do in a special way is that the sender and the recipient should have a private channel. So it's also resolved in a quite complicated way. So that's it for the zero knowledge proof. I hope that you get the flavor, the idea of this technology, how it works. And if you want to dig into it, you may read a lot of data, a lot of information. I have this information in the reading and watching. So that's it for me. Thank you for your attention.
Thank you so much, Serhii. Maybe somebody have a question.
I think nothing is understood from this picture.
It's very hard for understanding the first time, I think. Okay, maybe the end of this topic and the end of this lecture, and see you soon. And please wait for our task for you and for this presentation. Thank you so much.
Thank you.
Bye-bye.
Thank you. Bye.
Thanks.